Begin. Now, as I was mentioning, there are some variations to the vertical circular motion problem that we've seen with a particle attached to a thread. So we will look at Bhargav, in the last class we have done vertical circular motion in a lot of detail, and I've just sent the notes and the recording of that session, so you can go through that. So let's start with another example of another situation of vertical circular motion today. So now we have this kind of situation. We have a smooth hemispherical surface like this. So this is smooth hemispherical surface. With a radius of 20 meters. Yes, Harsh, this will be the last lecture of circular motion. Now what is happening is that a particle is initially at rest over here at the point A initially and is given a slight push. So it just about starts to slip, and after some time it reaches an angular position theta like this with respect to the vertical, and by now it's got a speed v. So a particle of, let's say, mass 2 kilograms initially at rest at the point A slips off like that. Okay. And at the position, let's say B, its angular displacement is theta with respect to the initial position A. So first of all, we have to find the speed v and the normal contact force. Okay, both of these as functions of theta. And secondly, find the value of theta at which the particle loses contact. Okay. And then the position at which it eventually hits the floor. So, somewhere here, if the particle loses contact with the surface, and then it goes into a projectile motion. So it hits the floor at some point P like this. So let's say at some point D like this, it loses contact in the diagram. And then it goes into a projectile motion and hits the floor at some point P like this. So you have to find the position of that point P. Yeah, Norman will discuss. After completing few of these problems, we'll discuss H.C. Verma doubts, both from circular motion chapter as well as vertical circular motion from the work by energy chapter. Because vertical circular motion problems in H.C. Verma are in the work by energy chapter. So start with the first part of this. This is very easy. Remember, it's a smooth surface, so no frictional force. So mechanical energy conservation will apply. So after completing this problem and couple of more problems, we will probably in about half an hour's time, we will switch to doubt solving from H.C. Verma for circular motion. We'll try to complete the doubts today so that next lecture we can move on to the next chapter. Okay, so first let's understand the geometry of the problem. So the particle started from this position A, its speed was 0, and by the time it's come to this other position, let's say B, which is at angular displacement of theta, by the time it's here, it's got this tangential speed V, because it has lost gravitational potential energy and gained kinetic energy. So you can see that at any point like this, the forces acting on it are two in number, which are mg and normal reaction. And you can see mg is the conservative force which is doing positive work. Hence, its potential energy is decreasing. Whereas normal reaction is a force which is not doing any work, because it is perpendicular to the instantaneous velocity. This angle is 90. So work done by normal reaction will be 0, because normal reaction is perpendicular to displacement. The instantaneous displacement is velocity into time, like this. Okay. So therefore, we take the earth plus the particle as a system. So we can say that change in kinetic energy plus change in gravitational potential energy is 0, because work done by external force is 0. There is no external force doing work, and work done by non-conservative force is 0, because there is no friction. Okay. So now when we apply this from A to B, you can see the change in kinetic energy is plus half mv square, but the change in potential energy is minus mgh, where h is this height. Okay. So now all we have to do is substitute the value of this height in terms of theta, so that we can get v as root 2 gh. Okay. So in that we need to find out how much that h is. So for that you have to just look at the geometry of this triangle. This triangle. This is r. So this is r cos theta. So h is equal to r minus r cos theta. Okay. So this becomes the answer to the value of v as a function of theta. Okay, now write the dynamical equation and get the normal reaction as a function of theta. Okay, now let's understand the free body diagram equation. So if you just look at this particle on this surface right now, this is the normal axis, this is the tangential axis. So on resolving the forces, you don't need to resolve normal reaction because it's already like this, but mg will get resolved into mg cos theta and mg sin theta, and the particle has centripetal acceleration and tangential acceleration. So mg cos theta minus n is equal to mass into centripetal acceleration. So that's mv square by r. So from this equation we'll get n as mg minus mv square by r. So this is our second equation, whereas this was our first equation. So now you substitute this here. From the first equation, substitute v as, or v square as, nobody pointed out to me that I missed out the 2 over here. It's square root of 2 gr into 1 minus cos theta. So be alert about these things. Okay. So make sure you've noted this down. This 2r, not r, because h is equal to r into 1 minus cos theta. So substitute that here. So we'll get normal reaction as a function of theta as mg minus m by r into v square, which is 2 gr into 1 minus cos theta. So finally, this will give us normal reaction as a function of theta as mg into this mg cos theta. Again, I made a mistake. So n should be equal to mg cos theta minus mv square by r. So that is mg cos theta minus this term. So finally, n will become mg into 3 cos theta minus 2. So this is our normal reaction as a function of theta. This was our v as a function of theta. Okay, so I'm just minimizing this a little bit. Just make sure you understand all the steps. Okay, so now that brings us to the second part. We have to find out at what value of theta normal reaction becomes zero. That is, the particle loses contact. Okay. So by the way, in this m is 2 kgs and g is 10 meters per second square. So normal reaction is 20 into 3 cos theta minus 2. And similarly here, r is equal to 20 meters and g is 10 meters per second square. So v is equal to square root of 2gr into 1 minus cos theta. So numerically v's value is 20 into square root 1 minus cos theta in meters per second. So we'll be requiring this in the second part. So we'll see that particle loses contact when normal reaction becomes zero. So n, which is should become zero. So that means 3 cos theta minus 2 should become zero. So cos theta should be 2 by 3 or 0.67. So theta is cos inverse 2 by 3 or cos inverse 0.67. So this becomes the answer of this part. Okay. If we want to calculate it numerically, we can always use a table or a digital camera, digital calculator, scientific calculator. So it's about 48 degrees. Okay, so that's that. We have done this. We have found the value of theta at which. Now the rest is we have to solve for the projectile motion, the position where it eventually hits the floor. So for that we have to use the projectile motion. Yes, you're not taught in the sense that uh, I mean it's just a function in a scientific calculator. If you like, I can show it to you. So you can see here I have a scientific calculator, right? So what I have to do here is I will first type 0.67, right? So I've typed the value 0.67. Okay. Then I will type this shift button here. Okay. So shift. So that gives me the inverse function. I want to do cos inverse of that. So I'll type cos. So you can see it's giving me close to 48 degrees. Okay. So similarly, if I, for example, if I type 0.5, now you know that cos inverse of 0.5 is how much? It is 60 degrees. So let's work it out. So I will type shift, that is inverse function of cos. She is giving me 60 degrees. If I type cos of this, it will give me cos 60, again 0.5. Now if I shift and type sine, so it will give me sine inverse of 0.5. So that's 30 degrees. So again, if I type sine of 30 is half, but sine inverse is 30 degrees, like that. So if I basically type 2 by 3, okay, so that will give me a more exact value. So 2 divided by 3, that's equal to 0.666, like that, 7. Now if I type shift of cos, that will give me cos inverse of that. So that is 48.18 or approximately 48.2 degrees. So this is how we use the inverse function in a scientific calculator. I just have an Android scientific calculator in my phone. You can just look for any Android, or if you're using an Apple device, then any Apple app, which is basically a scientific calculator. Download it for free and just install it. Then you don't need a separate calculator for doing it. Okay, anyway, let's get back to the question. Now the next thing is we want to solve the projectile motion part. So this is a bit of like a revision of kinematics for us now. So we know at what position it is losing contact, and we also know what is the speed when it is losing contact. Okay. I'll just use this diagram. So now in this diagram, the only thing I'm interested in is the kinematics part, that is the motion part. So I'll remove off all the unnecessary things. I don't need the forces and all. So this is the position from which the particle is leaving contact. That is when that angle theta is about 48 degrees. So from here it will go into a projectile motion. So the path of the particle will be like this. So from here we will solve it as a projectile motion. Taking this as our origin, this as our x-axis, this as a y-axis. So this point was our point we had called D, where it lost contact. So this theta was cos inverse 2 by 3, or approximately 48.2 degrees at D, when the particle loses contact. Okay. So further you can see that over here this angle is also theta. So this angle here is also theta. So that speed v, which was 2gr into 1 minus cos theta. So this will become square root of 400 into 1 minus 2 by 3 using this value. So v is 20 by root 3 meters per second. So this v that we have, this becomes the projection speed. Okay. And theta is the angle. Okay. Below the horizontal. Okay. So now the particle is going from that point which we are taking as the origin of our new coordinate system, and it's hitting the ground somewhere over here, the point I'm trying to show below. So wherever it is hitting the ground, if we now take this when it started from here as our time t equal to 0, then it comes and hits the ground at some point of time t equal to capital T, let's say. So during this time, what is happening? Its acceleration is g downwards and horizontal acceleration is 0. Okay. So for the projectile motion, from O to P, what is happening is that ux, the velocity v, has components v cos theta and downward component cos theta is 2 by 3, then sin theta can be easily calculated like this. Okay. So that is root 5 by 3. So the x component of displacement is ux into time. So that is, and the y component of displacement is uyt plus half gt square. So that is, this is the y component of displacement. So now you can see that this distance is r cos theta, okay, and this distance is r sin theta. So if this distance is now d, okay, then we can see that at time t equal to capital D, x is equal to d. That means and y is equal to r cos theta. So this is our second equation. So now this is how we have to solve for that distance d, so that we can find the position of that point P. So to find position of the point P, we need to find that distance d. So from equation 2, we'll solve to find capital T. Okay. And then substitute that in equation 1. So we'll solve to find small d. And that's it. Once you found small d, you know the position where it hits the ground, because from here to here, from the center of curvature to that point, you can see this distance is r sin theta. So from the center of curvature to the point P, the distance Cp will just become r sin theta plus d, which you can then find out. Okay. So I'm not getting into the full solving because it's a quadratic equation with some square root terms and all. It will take some time, but this is the method of solving it. So the earlier two parts we did 1 and 2, they illustrate an important variation of vertical circular motion, where instead of a particle being attached to a thread and doing a pendulum kind of motion, we have a variation of that where a particle is sliding down a hemispherical surface which is smooth. Okay, so hope this is clear. Now let's look at another variation problem. This is another important type of vertical circular motion example. Now in this, suppose we have a kind of a tube. Let me just finish making this then. Yeah, so we have this kind of a tube. This is a narrow tube fixed in a vertical plane. Okay, so we have fixed it against something like a wall or something in a vertical plane. So acceleration due to gravity g is like this, and both its inner surfaces are smooth. It's got smooth or frictionless inner surfaces. Okay. Now what we do is a particle that just fits into the tube is placed inside it and initially placed over here. So the tube is circular in shape of radius r. Okay. So this particle is just about released from this position A. So its initial speed is just tending to 0. You give it a slight push, so the speed is tending to 0. So by the time it comes to this point B, and later it crosses this point C, so a particle of mass m which just fits the narrow tube starts from the point A with u almost equal to 0, u tending to 0. So first find speed and normal contact force at B. Okay. Find speed and normal contact force at C. Okay. Now next we'll also see find theta at a point D such that the normal reaction is 1/3 the weight. Okay. And the particle is in contact with the inner surface, or B, the outer surface. So what we mean by inner surface and outer surface is that the particle might be like this. So it's resting on the inner surface and the normal contact force is like this. Or it might be at a point like this where it's resting against the outer surface. So the normal contact force is like this. Okay, this is in contact with outer surface. This is in contact with inner surface. Okay. So anyhow, start with the first and second part. They're pretty easy. So again, the tube has no friction on the inner and outer surface, both. Both are smooth surfaces. So you'll be able to apply work energy very easily. So this time, because it's a tube, the particle doesn't fall off from the surface like in the previous case where it was slipping on a hemispherical surface. The outer surface of the tube keeps it in that circular track. Yeah, anybody got the answer? Yes, very good, Deep. Your answer for B point is correct. For C, your V is correct, but normal reaction you have to check once more. You might have made a mistake in calculation. Just check. Or you might have taken the direction of centripetal acceleration wrong. Just check. So you got 3 of the 4 things correct. The last thing, the normal reaction at the point C, just check. Yes, very good, Deep. Now it's correct. So I'm just showing the basic method of calculation for everybody else also. So now we just concentrate on the motion between A and B. Forget about the other things. So A to B, you can see that the change in height is equal to R. So A to B, change in kinetic energy plus change in gravitational potential energy is 0. So half mv square minus h is equal to R. So substituting, you will get V is square root 2gr at the point B. Now once you get that, now you can see the forces acting at the point B are normal reaction and weight. So normal reaction is acting like this. It's in contact with this surface, so it's pushing it inwards. Okay. It's in contact with the outer surface. This one is the outer surface. This one is the inner surface. For example, when it starts out at A, it is in contact with the inner surface. So somewhere in between A and B, it switches its contact from the inner surface to outer surface. So anyway, this will provide the centripetal acceleration and this will provide the tangential acceleration. So N will be equal to mass into centripetal acceleration, or mv square by r. Okay. At B again, and mg will be equal to mass into tangential acceleration. So substitute this now. So N will become 2mg and tangential acceleration will become g. So notice one thing, that this is the maximum tangential acceleration. Whereas the same thing by the time you come to C, for A to C, the vertical displacement is 2r. So V becomes square root of 4gr, or 2 times root gr at C. Okay. And now if you look at the forces at the point C, normal reaction is acting inwards like this and mg is acting downwards. So again, it is in contact with the outer surface. The lower surface is the outer surface. So the outer surface is applying the contact force. It's in contact with the outer surface. Okay. So at the point C, you can see N minus mg is equal to mv square by r. Okay. And tangential acceleration is 0 because there is no tangential force. So N is equal to mg plus mv square by r. So now substitute this value. So N is equal to 5 mg, 5 times the weight at C. And this is the maximum value of N throughout the motion. Okay, very nice, Deep. We'll discuss. Okay. So now, if we kind of also keep in account what we had done in the previous question, the one with the hemisphere, we had seen that at any general point, D, theta is less than 90 degrees, that kind of point. Okay, we have V is equal to square root 2 GR, 1 minus cos theta. This was from work energy. Okay, and normal reaction was mg cos theta minus mv square by r. Okay, assuming contact with inner surface. Okay, that is here. If we assume that at the point D, the particle is resting against the inner surface, so the inner surface is applying a contact force like this. Okay, so it's seen that this gives us this result. But at theta equal to cos inverse 2 by 3, which is approximately 48.2 degrees, n becomes 0. So what this means here is that, so what this now implies is that for theta between 0 to cos inverse 2 by 3, normal reaction is non-zero, but contact is with inner surface. Okay, so that means normal reaction is radially outwards, okay, like I've shown in this diagram. But the moment we cross this point, for theta greater than cos inverse 2 by 3, normal reaction again becomes non-zero, but contact is with outer surface, like we saw for the point B. Okay, so normal reaction is radially inwards. Okay, like I'll show a point E over there, but this point D labeled in my diagram. So further down somewhere over here, there can be a point where this is what is happening. So that normal contact force now at this point, you can see will be radially inwards. Where it's in contact with outer surface. Here it is in contact with inner surface. So when this happens, the formula of normal reaction will become n plus mg cos theta is equal to mv square by r. So n will become mv square by r minus mg for such a point. Whereas for such a point, n was equal to mg cos theta minus mv square by r. This kind of thing. Okay, so this is the analysis. Now from this analysis, you have to find the value of theta at two particular positions where the normal reaction's magnitude is 1/3 of the weight. But in one case, it's in contact with the inner surface. In the other case, it's in contact with the outer surface. Okay, so all the analysis that you need to be able to solve that part, I've given you over here. So just try to work it out yourself now. Deep, you have to check your second answer. Beta. The first answer is good, correct. Second answer, see, it's not feasible. Na? Cos theta cannot be greater than 1. So some calculation thing you have to just check. Okay, so let's look at the A part of question 3 now. So in the A part, the normal reaction should be equal to mg by 3 with inner surface, not the outer surface. Okay. So you want this kind of a position, like in D. Somewhere over here, so I'm just making a rough diagram. So we want that if the speed of the particle is v, mg cos theta minus n should be equal to mv square by r. So now this condition, so mg cos theta minus mg by 3 should be mv square by r. So v should be equal to v square, you can say, should be equal to gr into cos theta minus 1 by 3. This is the equation that we're getting from the dynamics. Okay. And then of course, starting from the point A where u was 0, particle has come in a path like this. So A to D, v square is equal to 2gh, that is 2gr into 1 minus cos theta. That's our second equation. Now you solve these two. So gr into cos theta minus 1 by 3 is 2gr into 1 minus cos theta. So 3 cos theta is equal to 2 minus 1 by 3, so that's 2 by 3. So theta is cos inverse, 2 plus 2 by 3. So that will become how much? 2 plus 2 by 3 will give us 7 by 3. So this should be 7 by 9. Okay, so this is this part. Now the B part,